Okay, welcome to the third lecture on learning-assisted automated reasoning. Last two times, we've introduced the theorem proving systems and machine learning problems. We discussed the lemma relevance problem in more detail, and I'm a little bit reminding this because essentially, as part of applying machine learning to automated reasoning, what we're going to be doing is doing something very similar to lemma relevance, but in every single step. If we think about what is happening in a calculus like the resolution calculus, we are selecting some of the previously derived clauses to resolve to factors. So we need to have relevance of these clauses for the proof, where again, by finding the proof, it's just the relevance for deriving the empty clause. But in the end, sometimes it may be useful to know which ones are the ones stemming from the conjecture and which ones are just dilemmas. That's why even if we are in this abstract setting, I will still talk about it as goal-directed. So that's why I'm reminding you the lemma relevance problem. And yesterday, we discussed resolution, variants of it, so how can we introduce ordering, what can we do about equality, how can we order equalities, and how can we start to combine equalities, therefore, as part of our reasoning, derive decision procedures for certain subfields. One thing that I was hoping to cover last time, and we'll move it to today, will be to actually see how does learning look like in a state-of-art superposition calculus prover, and then we'll extend this to a calculus which is more suited for learning, namely the tableau calculus, but also an advantage of the tableau calculus will be the fact that we are able to handle many other calculi. The advantage of resolution and superposition is the fact that we have a very simple way of thinking about what are the possible inferences, what are the possible steps to look at. On the other hand, just the most primitive real inference is classical. In order to justify the soundness of the resolution rule, I said it's either the case that our predicate holds or it doesn't, and in these two cases we're combining them. Non-classical variants of resolution would be very limited. They work only for very specific calculi, and therefore we need to look at something more, well, on the one hand refined, but on the other hand it seems simpler, just not as efficient as resolution. And then so far we looked at mostly supervised learning. We have a training set that was created based on the heuristics or based on human proofs, and we try to imitate it, but it would be much nicer to start without any heuristics and derive them, essentially going in the direction of reinforcement learning for theorem proving, and I hope to finish the lecture today with reinforcement learning and cover a little bit more of the open problems about it in the exercises. Okay, so let's go from the calculus to an actual full-scale superposition calculus prover. In order to do that, well, actually I have one more slide, which I wanted to talk about before. So where are we? We know how to select relevant knowledge. This is useful both in systems like eProver and Vampire, which perform some selection of the knowledge from a large ATP problem, but also in interactive theorem proving, where a user is interacting with a system to complete a proof, and there a selection of the relevant knowledge is going to help us use the automated techniques. The second thing, which kind of we have an idea how to do, is, we've discussed it in the exercises, we have an idea to extract some patterns, some shapes of interesting mathematical conjectures, and these shapes can be extended to new possible properties that could be interesting. So these are the two things that we kind of have. This one I discuss in more detail, that one we have an idea that this can be done. And in principle, it's not just statistical approaches, but you could train a neural network to look at all the shapes of statements in some big library and hope that it can use some RNN-style approach to generate more of these. Where we want to get is a more human-like proof. And one major thing is getting to this divide and conquer approach, where we are conjecturing intermediate statements, and this kind of conjecturing using even the generative approaches has not worked so far. But even further, where we want to get is auto-formalization, being able to, given a mathematical text, switch to having a fully formal statement in logic that is hopefully provable. And there's also a little bit of progress there, but the major problem is getting enough data to train the systems, is integrating the property of the calculus, such as like, I want to make sure that the thing that the system generates does type check. And so, yes, we can do some masking in a network that does it to not allow non-type checkable expressions, but at the same time, does this make sense? Is it something that the network could learn? What can we put on which level? What makes sense? Lots of trials and errors, nothing that works very well, but quite a few papers on this topic in the past 2-3 years. Right. One thing in between would be actually applying machine learning to individual step selection. So let's now, in the first 1/3 of the lecture today, talk about doing this for eProver and what do we need to do it in eProver, what do we need to do it in a complete superposition calculus prover. I'll first, on one slide, remind you the components of such a prover. And the components of such a prover would be first the calculus, then lots of optimization, some of these we've already discussed, and implementation. So typically, people are trying in various ways to improve a system that they have. This has been motivated, justified by the existing competitions, and there are various ways how you can improve a system. You can improve it by improving the calculus. You can improve it by extending the technicalities around it, so getting rid of subsumed things, some indexing things, and so on. But there is also quite a lot being put into engineering. Each of those gives you a certain kind of factor of efficiency, and it's typically that each of those gives you essentially an order of magnitude when it comes to the speed of inferences performed. Well, I'm talking about inferences in the sense that a better calculus lets you avoid 90% of the inferences. So no, it doesn't make it 10 times faster, but rather lets you skip a lot of important things. The good techniques around it give you the same thing, and an implementation actually makes it 10 times faster. However, typically, just doing a better implementation is not able to cover up for a bad calculus. So the order of the things here, I tried to put them in the important order, but essentially there are these 3 classes: the calculus, the things around it, the heuristics, and finally the implementation, and the lower one cannot cover up for the problems in the higher one. Since the late 90s, the superposition calculus has been the main technique for first-order theorem provers, and nothing has been able to beat it. But you can get something that is 10, 15 times 10 to 15 times slower, and therefore worse, being able to solve, let's say, half the problems if you skip the other parts. Right. The calculus, then subsumption, and we've discussed subsumption yesterday when it comes to standard first-order reasoning, but you have to extend subsumption to clauses that have equality. Again, if you're able to do a rewrite in 2 steps, that's better than a rewrite in 1 step followed by a rewrite in the 2nd step. So there you need to think about what is the meaning of subsumption when it comes to equality. And when it comes to already the simple subsumption, we're looking for things that are more general and shorter. So here, this requires some intelligent indexing structures. So looking for supersets of an expression, that's pretty much what something like Google does, right? We have 3 words and we're looking for a web page that contains these 3 words. So you can imagine that various finger trees or whatever could work there, but they're not going to be particularly efficient. And in fact, today, a number of machine learning style indexing structures are working pretty well. So things such as feature vector indexing, where you have features of clauses that let you find candidates for subsumption, would be used. So that's one thing, and this indexing, of course, has to be extended further. The same thing for tautologies. You want stronger tautologies, and I have mentioned ideas coming from congruence closure. Orderings, I've said we have ideas about orderings, but how to select an ordering for a particular problem. That means we can try to build a portfolio, but just combining a number of different strategies, but you want to detect that something is a group, and therefore this kind of ordering is going to complete the group immediately and solve lots of problems very quickly. So these heuristics for the orderings, heuristics for literal selection, heuristics for various things in the prover, we need to have pretty good ones. And finally, implementation. One exciting thing that I'll give you as an example of an particularly useful implementation feature that is done in eProver would be the fact that you not only share all the terms, but also every time you perform a rewrite, every time you replace A by B, you replace the A by B everywhere. So the chalk is missing. Maybe here. Here it is. So every time we have an equation that is A equals B, and this equation would be oriented, so we will be replacing A by the B. Let's say I have a term f of A and something else, and then I have another term. There's only one occurrence of A in the whole memory. Therefore, after such a clause is derived and it is oriented, all the links that somehow link into terms that have A as a subterm will become replaced by terms that have a B as a subterm. But that means that we had a number of properties of such terms. There was a term f of A of something. It was somewhere in the ordering. Some things have been computed about it. Some weights have been computed. So you have to mark that there are some things to be updated as soon as this is encountered and so on. So this is a pretty high investment when it comes to engineering to set this up. But at the same time, this is precisely what does give you this one order of magnitude of efficiency. It requires a parser that is able to recover everything very efficiently, have all the terms stored in kinds of term banks that let you, as soon as you've performed a rewrite, be able to recover all the shares and make it unified and so on. In fact, Vampire for a long time would include its own garbage collector, which means garbage collecting terms of this kind can be done more efficiently than it is done in general, so you're deallocating it differently. Okay, so that's it when it comes to what constitutes a modern superposition-based prover. We have all the components. We've seen an idea roughly how does something like resolutional paramodulation do, what does it do if we're doing it manually, what does the prover do? Well, it starts with a set of unprocessed clauses. This would be our problem. And an empty set of processed clauses. It performs now a number of rounds where in every round it's going to select one of the unprocessed clauses and process it. That means there are a number of things performed about the clause, various kinds of simplification, because maybe something could be done now that we have more information, and we are combining the unprocessed clause with all the processed clauses, right? These are the ones that we've already dealt with. The invariant that we're trying to preserve is the fact that all the processed clauses are processed with each other. So there are no new inferences that can be performed by combining two clauses from the P set. Every time we're moving one clause U to P, generating a number of new clauses by combining them, and then the new ones are moved back to the set U. This means that our set U is growing. Every time we're processing things, the set U is growing by a number of new generated clauses, but hopefully it could also be the case that some of the unprocessed clauses do not give rise to new things, that there is no possible inferences, or the things that are derived can immediately be simplified, and therefore there is nothing new added. So there is some uncertainty as to how these two sets grow, but in principle we have two growing sets. We have a growing set of processed clauses, growing set of unprocessed clauses. A number of things can happen. One thing that can happen is we have derived an empty clause. We are done. The other thing that can happen is we've processed all the clauses. This means in the calculus it is not possible to derive the contradiction. This can mean two things. Either we are complete, and hopefully if we are doing just plain superposition calculus, we are complete, therefore this means the problem cannot be proved. The word in first order vocabulary would be it is counter-satisfiable. Or if we have some kind of incomplete search strategy, then we don't know, we need to look for something new, but everything that we've derived, well, is definitely true, right? Soundness is definitely not lost. Okay, so what would be the main choice here? Well, this was discovered a long time ago, about 50 years ago. It was discovered that the main choice is the selection of the next clause to process from the unprocessed clauses set. Why? Well, our proof is going to be the final proof, the somehow reduced final proof, is going to be a sequence of inferences, and if we select the clauses to process precisely in the size of the proof, then we've done only the number of steps that are required for the final proof. If we process other things, if we select, let's call it wrong things, then this can be arbitrarily big. We can usually go into some infinite wrong loop. So a lot of heuristics have been defined for selecting the right clause to process. The two most important heuristics that's in the 70s and 80s that have been tried would be the heuristic to choose the smallest clause. Sounds very reasonable, right? We want to derive the empty clause, so if we try with the smallest one, we're hopefully going to quickly derive the smallest possible thing there for the empty clause in whatever metric, right? We have to define a metric on the clauses and just number of literals plus the size of each of the literals in a way, for example, that the weight function is defined. The second important heuristic would be to process the oldest clause. The oldest clause is definitely complete because we have just a FIFO, right? But at the same time, it's horribly inefficient. At the same time, the heuristic that selects the smallest clause is surprisingly inefficient by itself as well. So what was discovered for the first time in the prover 9 prover would be to combine the two, to select a number of oldest ones and a number of smallest ones, interleave between the two, select 1 and 1. So we have these two priority queues, right? This was the first thing done in the prover 9 prover, and it's still there until today. We have this ratio between the one and the other being 1 to 5. So we select 1 oldest and 5 smallest. This gives a pretty good strategy in itself. For a modern prover like eProver, we would have a complete strategy language to describe how things are pulled from here. And this strategy language would have strategies that include 14 different queues where we're pulling a few from here, from here, from here in a very strange order, and this comes out to be quite efficient. So what I'm trying to say is this used to be the most important decision 50 years ago, and according to Stefan Schulz's paper from 2015, it's still the most important choice today. How do we select this queue? So how about we try to apply deep learning to select the next clause? And what we can do about it, what is the problem? We have a number of clauses. This clauses is some, let's call it, huge library. And from this huge library, I want to select the thing that is most useful for the proof currently. Well, this reminds us of a problem that we've covered 2 sessions ago. This is essentially almost the premise selection problem, and essentially what the deep math research tried to do can be almost applied here. So what can we do? Well, we first let's give the setting. We need to gather some data. It was first done in this supervised setting. So we selected the MESAR top-level TRMs encoded in FOF. This means we have 32,000 MESAR TRMs with more than one proof, which we split into a training validation sets. And an important thing is these are the proofs that people managed to get somehow, but it's important that we're able to learn from them. Therefore, all the proofs have to be in the same setting, so they need to be replayed with one strategy, and something like 1% failed to be reconstructed with a single strategy. Even after we know how to do the proof, the single best strategy cannot deal with it. It sometimes happens that it would just be too long. Even with something like half an hour timeout, you will not get it. Collect all the intermediate steps in CNF, and this serves us this training data. So let's see how well does it perform. Well, okay, before we see how it will perform, let's specify some models, how we're going to train it. And the deep networks would be very similar to those considered in the deep math research. So we are essentially embedding the current clause, concatenating it with the conjecture. So what is the proof that we're actually trying to get, and have a fully connected layer to get a single classifier, okay, regressor here, so a logistic loss to find which one is the most useful one here. How does the embedding work? The embedding would be 3 layers of convolutions. Well, convolutions followed by nonlinearity and max pool on top. One thing that was tried at the time, this was done roughly 2 years ago, and at that time one thing that came up was this WaveNet research, where performing dilated convolutions gave better results for some domains, for auditory domains where there is some distance between the samples. So this was also tried here to, instead of convoluting the neurons that are next to each other, we do it for some that are distant by 2, 3, 4, and so on. Actually, it was only by powers of 2, so 2, 4, 8, and so on. This way, recovering the possibility that parts of a statement that are further from each other can start interacting. I will come back to this point. We are combining an embedding of the clause with the embedding of the negated conjecture. Right? Okay, let's let me give a general comment about the thing. I mean, we'll have an exercise, and that will be the first exercise of the exercise session today. Will be what's wrong about this setup? How can we improve it? And well, that's one thing that can be discussed. But a number of different setups have been tried. In principle, the idea here is we can completely forget about the right leg. We are doing tokens of the class, we're embedding them, and then putting a single one-layer classifier. Sorry, what is it, like a regressor? But yeah, so we're just trying to get a single value out of an embedding of a class, and this embedding should already have, as part of it, the information how close to a proof it is, how close to the empty clause this is. This is the only information we want. So in principle, if you forget about the right leg, this can be explained. Now, I will still explain the right leg. What's the point of the right leg, right? So we just want the information how close we are to a proof. So what's the point of putting the conjecture here? The conjecture is not relevant because we are trying to get to the empty clause. But it comes out that even if we are reasoning on the axioms from a library and trying to derive the empty clause out of them, the information which one of them has been the one that we are trying to refute, has been the start, is significantly helpful. It's not completely clear why. In a very simple setup, yes, because I can just compare if it's the same thing, and then we are closer to the thing. But as soon as we have a meaningful realization how provable the thing is, this should no longer be necessary. But the network, given the number of training examples, given the amount of training, could not learn a stronger relation. Right. Okay, so I've explained this part already. Okay, so let's now. Right. So these were essentially two models. So just a plain CNN and CNN with dilated convolutions, and the other thing that was tried would be to use a recursive neural network model to essentially build a tree model of a formula. So we have carried representation of first-order statements where we have an apply node, and there is a network corresponding, well, not a network, there is a cell corresponding to the apply statement, a node for or, a node for not, and these are shared across different formulae, and the weights are learned jointly for the same formula and across different examples, but at the same time, the structure of the network would be different everywhere, depending on the shape of the individual formula. Right, so we're doing this essentially like a tree model. This is much more natural when it comes to logic. We actually have a shape of a formula, and we hope that these applications work. And for propositional logic, such a tree model was very good. Charles Sutton showed last year at iClear that you can realize the equivalence of propositional logic formulae of size up to 20 symbols with such a tree model up to 95%. So it could really learn very well to distinguish if two formulae are equivalent, and therefore just by saying if it's equivalent to truth, you have the same thing as probability relation. So this is quite nice. For first order logic, he didn't manage to get it, is what he told me, and also here this doesn't seem to be as well, as we are going to see. Looking at the accuracy of the models, there should be a bolded. Oh yes, here it is. So this dilated convolution style network, this dilated convolution model would get an 80% accuracy, but the accuracies of the models on a 50-50 split would not be that different from each other. And they're in principle good in the sense we are above 50%, but at the same time, well, what is 80%? I mean, we want to know what is actually useful for a proof and what is not. I think as a human, I would have a better intuition. I don't know, but because I haven't looked at thousands of formulae, I've looked at 5 of them, but looking at 5, I do have a pretty good intuition what is useful. So here, well, this is a little bit of a disappointment, but having stared at these models for a month, well, you have to give up on this at some point. This is the best that our current models can do. Let's see how it performs in practice. So, and there are a number of things here. The performance becomes an issue. So evaluating a neural network at every step of where we are adding a clause to the unprocessed clauses step becomes too large of a burden. So you need to introduce some kind of batching where you're evaluating the things together as soon as there's enough of them, and therefore creating a queue out of that. The second thing is it comes out that even then it becomes too slow to be usable in practice, so you want to combine it with the best heuristic that is present in eProver. So we're creating this so-called hybrid heuristic, which combines the auto mode with the TensorFlow selected best clause in the way this has worked normally. So it's just a new queue with the same weight as the weight given to auto. So the same number of clauses are pulled from the machine learning guided clauses, and the same number of clauses are pulled out from the best heuristic. Okay, so what happens? Well, just what it learned seems to flatten out not very well as the number of processed clauses increases, but if we increase things, it seems to do better. And then if we compare the models to standard auto, quite early you are much more precise, but then later on the difference starts to diminish pretty fast. Should I zoom in on this? I mean, like, I think I said what you could see if I zoomed in on the graph, so I will leave it at it. So this means, well, we can do better, but does this doing better a little bit actually help with individual new proofs? Let's have a look at this. And so what you can do, I could have actually simplified this table a bit. What you can do if you are doing premise selection using a deep method, when it comes to some hard theorems, seems to be 1400. What you can do by doing the selection on the level of the individual clauses, so as part of running of the prover, would be a little bit more, but not significantly more. If you combine the two, so pre-select things in advance and then select them more precisely, you're getting a number that is finally a real meaningful one. And so in the end, the combination of all these approaches proved 7% of so-called hard measure statements. What is meant by hard measure statements is statements that have not been proved by an unmodified prover yet, right? So the library has, the measure library has something like 60,000 theorems. About 25,000 of them have not been ATP provable, but we have ITP proofs of them. These ITP proofs are often long. They include, in some cases, human written 1,000 steps. So these are pretty hard to invent, and many of these steps between the intermediate steps would be quite long. But at the same time, apparently 7% of these could be proved by guidance. That's a neat result. But, well, we're still not there. We're not able to do as much as humans can do, and the human intuition is still unbeatable when it comes to these. Okay, so that's one thing. This is quite nice, but what could we do somehow better? What could we do somehow differently? And let's think about, well, I'll have a flying slide that's like this AlphaZero silver thing, which you've probably all heard about quite a lot. I'll simplify that research by saying, what are the things that, in my opinion, AlphaZero does well? First, it does Self-play, using a learned strategy. So far in theorem proving, we have not done self-play. We've only looked at proofs done by humans and only looked at proofs done by heuristics that were human invented. Repeated strategy improvement, essentially reinforcement learning. There's nothing that stops us from doing that for theorem proving. There's some searching of the game tree, so there's the whole Monte Carlo aspect, which again for theorem proving has been somewhat neglected. We have mostly focused on methods that are using heuristics for selecting the interesting branches, and then well, what actually AlphaGo, AlphaZero did is that there's a separate estimation of policy and value, and well, policy does not converge, value converges too slow, but if you have one learning the other, then you get the thing working well. In principle, this is not necessarily yet an issue for theorem proving because we're not even doing any of these, but well, let's try to imitate it. So can we do all of this for theorem proving? I actually said most of these when looking at the slide, but what would it mean to do self-play? It means we have developed a strategy. So for example, our eProver style learning, can we redo this using a learned strategy and learn from the proofs obtained there? Maybe we are now exploring a different part of the space. Second thing, can we search the tree more wisely? So there's some rules of the game that we've been following. We're still following the eProver loop that pulls in one clause from the queue, but this is not how searching of a game tree looks. We have a number of moves and we're exploring some of the moves deeper, some of the moves shallower, rather than having an ordered queue of things. Maybe one could be to an extent simulated by the other, but the priority would have to be significantly modified. And the last thing, the estimations. Well, we had some idea about estimating the I think it's the moves, right? If you think about what was done for eProver, but estimating the move was done by estimating the state, so this was actually value learning rather than policy learning. So what is the issue here? What would be the issue if we wanted to do this? Well, I think the main issue first is the fact that in a game, we typically have a finite number of moves. In Go, there is, 20 by 20, roughly, moves, whereas for theorem proving, we have our set of clauses that grows, and this growth is uncontrolled. We have to select things among a set of moves that is sometimes is going to be 1 million, sometimes is going to be more than that, because for the actual unproved theorems, so for things like in proofs like the aim conjecture, the found proofs will be of the size 1 million, therefore the unprocessed ones would be hundreds of millions. So, and there's a question, what went wrong with eProver? But like I'll keep this question for, well, maybe I phrased this question wrong. eProver is a great prover in itself. The idea to apply deep learning there is perfectly fine, but can we do better than what was done on the previous slide? So for the rest of the talk, I will focus on the connected tableau calculus as implemented by the lean cop theorem prover. Warning, the name lean has multiple uses in theorem proving, so don't confuse lean with lean cop, abbreviated as lean. So, right. So for the rest of this talk, I'm talking about lean cop whenever I mean lean. It's based on a connected tableau calculus, so it's different than the superposition calculus, and I'll explain on the next slide roughly what is the meaning of the calculus. It is goal-oriented, so we're naturally focusing on the goal and trying to extend the goal rather than trying to find a contradiction in between all the axioms that we have, which means it's convenient for large theories because we're really starting with the most likely issue that we have. And in the yearly automated theorem proving competition, it regularly beats two major superposition calculus provers, despite the much more involved calculus with more properties, it's performing reasonably well, not among the winners, but among the, let's say, lightweight theorem provers. It has a compact Prolog implementation, which means it's rather easy to modify. It's so compact that I think during the Pro seminar, I'll even show it to you. It fits on a single slide. And there are variants for other foundations. I've here listed the intuitionistic version and the version for model logic, but in talks of Wolfgang Biebel, he would mention something like 20 different calculi for which connection tableau has been implemented. And one exciting thing about it is that it is the prover for which first experiments with machine learning have been tried. That's coming in 2 slides. Okay. So let's see the calculus. The calculus is pretty simple. There are essentially 2 rules. There's the axiom rule, which is trivial. As soon as we have an empty clause, we are done. So I am not going to even list it as an important thing. There's a reduction and extension. Reduction means if we have considered a certain decision, if we've assumed a certain thing on the branch, and we are still supposed to prove it, then we are allowed to close that branch. And extension means if we have a clause with a literal, where is this? If we have a C with a literal L1 to show, and this L1 unifies with an L2 being a clause in the matrix. We remember matrix from 2 sessions ago. So in our clausal form of the problem, then we can attach a copy of the clause to our tableau. Okay, so there are these 2 things that can be done. We'll show it in an example. Hopefully, this will be clearer in a moment. If you have not seen Tableau before, actually, how many of you have seen Tableau before? 3, okay. If you haven't seen Tableau before, you can think of it as the DNF variant of resolution. So normally in resolution, there are 2 rules. There's the resolve rule and the factor rule, and essentially extension takes a clause from the original problem and lets you resolve your current goal with that clause. So this is a little bit weaker than resolution before. In resolution, we could take any 2 things. With extension, we are taking one of the original clauses. But this means that the counterpart of factoring has to be stronger, so the reduction rule is a little bit stronger than factoring. We have not just a clause, but each clause has some kind of history, how it has been derived. So what has been removed from the clause, and all these things can be factored as well. That's somehow the intuition of it. Let's see an example, and we'll do a larger example in the exercise session. Here we have a system of 6 clauses. And we'll try to show that this system is unsatisfiable. The way we do this is we select one of these clauses and put it as the top line in the tableau. Each of the lines in the tableau is going to correspond to one of the clauses. So here we have the clause P of X that is put as P of A. And I've already instantiated the X. At the beginning, it's uninstantiated, but as soon as we're going to perform more steps, this is going to come in. So here we have a P of X. Now, what can we do? Well, we can use the axiom rule. If it's empty, it's not empty. We can reduce it if we have something in our history. We have no history so far. Or we can extend it, so we have to extend it. So we're looking for something that is going to extend P of X. So we're looking for any clause in our original set. So we always look in the original set. It never grows. We're looking for something that has the negation of P. Well, here's our negation of P. Very nice. Then I put a copy of clause 2 in the second line. So here there's R of xy. P of X, Q of X, and this branch can already be closed. We are done with that particular branch. Now we have to do something about these two. So essentially, we performed one resolution step. Okay, now we have R of XY. Let's continue with this one. What can we do about the R? We're looking for a not R. We have two of them. Which one are we going to use? We're going to use the second one. So we put a not R of AX and or Q of X. Now we have an A here, therefore by unification the A goes in the upper part of the tableau. The whole tableau is quantified only in one place, right? So we have all the variables are immediately propagated. Now we have a Q of Y that we have to, sorry, it's the Q of X that we have to finish. And again, we're going to connect now the fifth clause. Here we have a not Q of B or not R of AB. This one is closed because we connected it with the Q of B, and this one does connect with our previous decision. So this is precisely the reduction rule. We know that we obtained this as a goal while considering these as goals before. So how do we do this? If you think again about things in the classical way, it's either the case that RAB holds or we will do something else. If it holds, then we close it with this one. Otherwise, we close it with something else. So we can consider everything below a certain node in a tableau under the assumption that that is the negation of this holds. So we now know that not R of AB, so we can close this branch as well. And we do the same thing for the second branch. I will not explain it. We'll try to do this in the exercise session. As soon as all the branches are closed, as soon as we have all the connections, so each of them has been closed by something above or is already empty, we are done. That means we've proved it in connection tableau. What's the relation to resolution? There are two things. One of them is, in principle, every extension step is a resolution by one of the original clauses. However, each of the factoring steps, each of the reduction steps could be a factoring, but it could also be that you have to move it a bit up. So it's a number of resolution steps followed by a factoring step. So it's, in a way, you can think of it as a more compressed way to do a resolution proof, but it's more compressed, assuming that you cannot resolve with anything else than our original clauses. So that's one thing. The second thing to observe is, if you think about it in the game terminology, what is the number of moves that we have? Before, we had a growing set of clauses. Here, we either have a reduction to do, and, well, there is kind of, it could be growing, but there's hopefully not too many of them. There's typically one reduction, maybe two. It never happens that you have more than two. Whereas the extensions, which is the main place, there the number of moves is constant. We never get more than was present in our original problem. And even if we're considering a library like the Mizar library, there's 50,000 clauses at the beginning, 50,000 theorems, so 100,000 clauses or something like that. We have 100,000 moves. This is still manageable. This is still on the range of what a system like AlphaZero could do. Okay, very nice. So we have a calculus in which we hopefully can do more. Okay, so what are we going to do now about it? Well, let's try to do machine learning. I'm sorry, this color got a bit gray. So the first experiment was done by Josef Urban in Prague of connecting an external advice system, the sparse network of Windows machine learning program, via some advisor to Linkop, which would select the extension step using some external advice. The implementation was quite slow. well, we had a Prolog intermediate program that would be 1,000 times slower. But one exciting thing that was discovered was the fact that it could avoid 90% of the inferences. So, well, there's a trade-off, right? We are 1,000 times slower to be 10 times faster, so we've actually lost things. But at the same time, we see the potential, right? We see that we can get another order of magnitude if we just include good, efficient machine learning in the framework. Okay, so this was 2011. So we had one thing that we could do, get some efficiency. The other motivation came from Jens Otten. Jens Otten, the author of LeanCop, said at the conference where this was presented, he said, well, you gave me a male cop, what about a female cop? And so 4 years later, there was a fairly efficient machine learning connection prover, so female cop, which included a very simple but very fast classifier. It was the naive-based classifier, so something like that I could explain in a slide or two the previous time, with a number of optimizations. And we've seen a number of optimizations that I showed on 2 days ago, but with further things done actually for the problem. This would already be good enough to get some nice things. Second thing that was a major issue would be how to compute the features. Computing the features was something that is rather slow. So what you want to do is you want to characterize things only in some approximate way. Look only at the top of the term, essentially something like a hashing function. Go to a certain depth along a number of paths to get a rough characterization of what does the term mean. The next thing would be to perform indexing, and this indexing needed to be very efficient as well. So since we had hundreds of thousands of different proofs, each of them with many steps, the first thing you would do would be to perform offline indexing, so try to identify everything externally and allow a new instance of female cop to read off the data that can be relevant only for the current problem. Since in the new problem, I will only have these 100 possible extension steps, I only need information about these. Since I have only these symbols, I only need information about the features that contain these symbols, so all the features would also have to be somehow second-level indexed so that we can have a small subset of the data. That would be the second level of indexing for the current problem. And the third level would be to integrate it in the actual ATP indexing structure. Whenever a prover tries to figure out which of the clauses could potentially unify, it uses an indexing structure, in this case a discrimination tree, and the discrimination tree, rather than storing the clauses, would store the naive-based data, so you can select these are the ones that we will try before we even look at the other ones, right? So that was the rough idea. We've discussed last time during exercise consistent classification and scholemization. The performance is about 40% of that of non-learning LeanCop, but it could prove a few more theorems. This is nice. We could do depending on the data set. On some more consistent data sets, it would be 15% more theorems proved. On some data sets, it would be 3%, depending on how consistent it would be. Quite nice. Okay, so this is nice. If we include even stronger learning, if we consider XGBoost or deep learning, the thing becomes too slow to be usable in practice. So let's see, can we do something better? Because we've so far still done supervised learning in this setting, but we want to get further. So could we give our Tableau to an AI game engine? And the answer is both yes and no. The proof search tree is not the same as the Tableau tree. Unification is the culprit. It can cause some of the branches to disappear. If you just allow a prover to build the tableau, and it's going to search the branches in an arbitrary way. By performing some of the selections in other branches, we will no longer be able to use all the choices. Some of the moves will now fail. Therefore, you have to transform the problem in such a way that it actually becomes a game tree. And this is clear from our point of view, but is it fine? Is it fine to change the game dynamics? If you think about machine learning done for something like chess or Go, you're not changing the way the moves are done. A human still plays in a certain way. These were the moves that the human made. We were still making the same moves. So most games stick to game dynamics, only tell it, well, do this move. And here we're transforming the problem. Is this okay? And the claim would be, it is okay, because even if the ATP calculi are complete, practically the strategies that find most theorems are the incomplete ones. So something like eProver would run 30 different strategies for a given problem, and 2 of them would be complete ones. All the rest would be incomplete strategies. The same is true for original LeanCop. It would do the same thing. It would have a single complete strategy. All the rest would be very efficient ones that find most problems, but skip some very narrow corners, and that's what the complete strategy is for. If this corner case is somehow low, we can still find it. If it's deeper, there's no way we can do it both efficiently and cover such cases. So in LeanCop, the depth of proofs with complete backtracking, so trying all possible options, is 5 to 7. But if we restrict the backtracking, we can get to depth of 7 to 10, and there's about 50% more proofs being found. If we were to just do completely random playouts, we can reach depth of hundreds of thousands, just will not find a proof. So we have to do some intelligent learning. Okay, so how are we going to do this learning? The first thing we do would be to, the first thing that was tried, this is K 2017, would be to define a Monte Carlo version of a prover, namely stick with restricted backtracking, so do the same thing that the standard incomplete strategies for theorem proving do, and there select the branches using Monte Carlo playouts. This improves on LeanCop, but not by a big margin, and the potential would still be limited by depth. So here there will be these playouts of depth 50 that say this is the branch that is most likely to succeed. Thanks to this information, one could select the one to explore first, and the selection of that one first would close the other possible moves for other branches. What could we do more? One can learn both policy and value. Here, well, there's essentially no learning. There is a heuristic for the how good a playout is. Unfold only useful branches. Do not backtrack, arbitrarily long playouts, and learn both proofs and luck thereof. I'll comment on this later on. So how should we search a tree? This has been an area of research in AI, and we are now going to transport this to theorem proving as well. So what is the problem? The problem would be the so-called multi-armed bandit problem. Do you all know the multi-armed bandit problem? Does anyone know it? 1, 2, okay. So what is the idea? Imagine you're going to a casino, there are 20 games there. And one game is roulette, where if you put money into, if you bet on green, then you have a certain probability that you're going to win, and you have a certain amount that you're going to win. You have another game, so you select the game that seems to have the best result. Okay, so I'm going to play this game. I pull the arm of my armed bandit. It like rolls. I'm getting some money, but well, it should be that I win once per 3 times. I pulled the arm already 100 times. I still didn't get anything. I think the machine is broken. I think my prior probability was actually wrong. the machine is actually worse than what it used to be. So I try another one, and for the other one, oh, here it's better than what I thought it is. Very nice, so I'm going to pull this one. But then I start wondering, there's yet another one. I haven't tried that one. Maybe that one is even better. I should try it a little bit, right? So we have a certain prior probability of a win in a number of games to select from, and we need to select the one that is going to be actually the best for the game, but there is also something hidden about it. And it comes out that when you are exploring a tree, there's a variant of this that is the best one, namely Monte Carlo tree search with upper confidence bounds, where one would look at the average number of wins for the node, so the sum of the wins divided by the number of games that we played. This is what we want in the long run. We want the average reward, but there's also some prior probability pi, the probability, the prior for a given move I. But we've played the move I n times, and we also have the sum of the times that all the moves have been tried. Therefore, this decreases over the number of times we have played the particular move. So we have an average reward plus minus some uncertainty, some confidence bound, and we're taking the upper confidence bound so that we are going to explore it as much as possible. The intuition behind the formula, it is initially proportional to the prior, and later the average reward dominates. Where do the wins and the priors come from? Well, this is initially a heuristic, but later on it can be replaced by a learned prior and learned reward. That's precisely what we can do. We can learn what one should do for the particular case. Okay, let's see how this looks like in practice for a theorem-proving problem. I'll try to slowly explain this. In our tableau, we've transformed the tableau search into a search of game moves. We start with a tableau starting axiom, and then I list only the pink nodes. What is the goal for the pink node on this projector? It's pink. So here, there's a certain goal that we're supposed to prove. For that goal, we have a number of informations. The first one, the P, would be the prior. So initially, we have 4 moves. The 4 moves correspond to the 4 possible ways to start extending our tableau from the starting axiom, the one of the 4 possible parts that originate from the conjecture. Each of them has an initial prior. It seems that the rightmost one is the best. It seems most likely to lead to a win. The leftmost one is the second, and then the other two, and we're trying them. We're trying them 1 time, 2 times, 3 times, and we're getting some rewards out of playouts that pass through these nodes. As we see in a moment, it comes out that the average reward for the leftmost one starts getting bigger than the ones for the rightmost one. Therefore, the number of visits at the beginning here would be the highest, but after a certain time, the leftmost one grows above it. The same thing is true for all other layers. So here, the number of visits for all these nodes sums up to this number of visits of the tableau starting axiom, but we go down, and again we have some priors. In this case, the leftmost ones and the pink one would be the 2 that seems most promising at the beginning, but the pink one was the one where the reward was again highest. Therefore, we start visiting that one very much. Here there was one where the reward was pretty high, but yeah. And we continue doing that. After 36 more levels of the tree, the theorem is proved. We are getting to we are performing the moves that corresponds to building of a tableau. another thing to, so what's the thing to observe? We have a branching factor of, well, 4, 7 something. The average branching factor for the whole library is 9, but we are getting proofs of the length 36. So it's really like winning in some hard game where we really had to select pretty well the moves, and these are being cut off pretty early because they're not likely to be useful. Is there a question? Right. We are focusing on one branch, and it does not matter which branch we focus on. Every time, we have to close all the branches. So in principle, you could choose and focus on the one that seems hardest or something like that, but it doesn't matter. Either way, we'll have to do all of them. So we can just do it left to right. Right. We establish a fixed order. More? This is clear? Okay, so we need to learn the policy and value. What would policy be here? Policy is which actions to take. Where do they come from? They come from the proportions of the visits in previous successful and also unsuccessful games. So here we have certain moves. They were visited, this one and this one were visited more often than others. This one was visited 10 times more than that one. Therefore, this should also be a hint that in future games, actions that look closer to this one should be visited 10 times more than actions that look like this one. So that's the idea. We're learning these proportions. So this would be the first modification from something like alpha 0, where you're actually looking at the visits, but here the number of possible moves changes. Therefore, we have to look at proportions. We're exploring less the actions that were bad in the past and more the ones that were good, which means we can also learn in a completely unexplored field. We have no information, but just by reaching to goals that are dead ends, just by closing some of the sub-goals, we learn both bad and good things, even if we haven't proved a single theorem. So we don't need supervised data here. We have one theorem. We're trying to prove Kepler's, not Kepler's, what is it? Fermat's last theorem. We just give it, it's exploring things, and just by getting successes and failures for small sub-goals, by closing some sub-branches and also failing here, nothing can unify. It learns both positives and negatives. For value, essentially what's the meaning of value? How good is a state? How close to a proof we are? We want to reward states that have few goals. This would be the initial heuristic, but essentially it does not matter. Even if you start with a heuristic of we won or we did not win, we learn as much. It learns this in one round, and it learns to reward easy goals in more reinforcement learning rounds. How are we getting training data for policy and value? Well, if we just look at our graph here, sometimes we have so few visits that maybe we don't want to consider such states. Therefore, what we do is we explore 1,000 nodes using UCT, starting from a starting node. This means now a starting node is a well-explored action, and we continue from that point. We select the most visited action and focus on it for this proof, doing again 1,000 explorations. Now we have a sequence of such selected actions. Such a sequence can train both policy and value. How does it give us policy? Well, we get policy because we get proportions in all these nodes, and we have at least 1,000 visits for them. So somehow these proportions are meaningful, and the same thing for value. We either won or lost, but having explored all the states on the way quite well, therefore we know that they're either good or bad, and we can give this as training data for value. Some comparison. I can do this before the break. What is the baseline on some 2,000 selected easy problems? plain lean-cop can do 800 of them, and plain lean-cop meaning it has all the heuristics that have been defined over 10 years by humans working on the problem. Well, maybe I should not say all the humans. There are maybe 3 people that work on lean-cop, so that's, I should not overestimate the size of that particular field. The theorem proving field is pretty widespread. There would be 1,000 people, but they all work on different systems, different calculi. So, yeah. Random playouts. If you completely ignore any policy or value, you get 430. And if you do UCT without any policy or value, just knowing which things fail or win without any learning so far, you already get 770. This is almost what Monte-Cop did, but Monte-Cop had some heuristic at the end. So here this is without any heuristic, we forget anything that was done. It's surprisingly good. It almost reaches what humans could do, so that's pretty cool. And if we add reinforcement learning from previous iteration, if we learn from this round, then we're getting 1,000 theorems proved, and in subsequent rounds it increases to 1,200. This is very nice that we can throw away the human heuristics, but I remind you, this is an initial comparison. The training set is the same as the test set, so this is one big cheat. So let's try to fix the cheat. Let's try to do it a bit more properly, split it into a training set and a test set. The baseline is roughly the same. 70% of what lean-cop could do can be done by plain UCT, and in 10 iterations on the training set, it is not monotonically, but mostly increasing up to something like 30th round, but with some hops down. And on the test set, you're still getting significantly better than what lean-cop can do. So this is pretty exciting, and we'll discuss the difference between the two and various other issues after the break.